Be honest, have you ever opened Chapter 1 of your Class 12 maths book, taken one look at that relations and functions section, and immediately just wanted to slam it shut? Yeah, I completely get it. It hits you right away with this totally intimidating, abstract alphabet soup of A's, B's, and R's. It looks like a completely different language, and honestly, it's enough to make anyone want to skip the chapter entirely. But hey, don't turn the page just yet, because today we are going to decode all of it together.
I want to completely flip the script for you here. What if I told you that the math alphabet soup you might be picturing is actually the exact same thing as, say, an Instagram family tree? Seriously, mathematical relations are essentially just the math version of a social network. In this explainer, I promise you we're going to master the core of this topic in just a few minutes, completely painlessly and without losing your mind. We're going to make this ridiculously easy.
Okay, let's dive into part 1, the connecting machine. We're going to step away from those dry coordinate pairs for a second and look at relations as what they truly are. To start, we really just need to understand a relation in the absolute simplest terms. It's just a rule. That's it. It's a rule that connects an element from one group, let's call it set A, to an element in another group, set B. That scary mathematical notation, A comma B belongs to R, it's literally just a super condensed way of writing A is related to B. It's just a bridge between two things.
And what's really cool here is how easily we can ground this abstract definition into something we understand instinctively. Imagine set A is a group of people, and set B is a list of countries. The mathematical relation, the rule connecting them, could simply be has visited. So if Sarah has visited Japan, they are connected under this specific rule. Sarah is A, Japan is B, and the bridge between them is just the act of visiting. It's a really simple, direct connection.
Moving right along to part 2, reflexive, the mirror.
Now that we actually know what a relation is, let's look at the big three. This is where students usually get confused, but we're going to break them down using familiar, everyday concepts. This first type is called a reflexive relation. The mathematical rule here is that every single element in your set absolutely must be related to itself. For every A in the set, the pair A, A must be present in the relation. I want you to think of this literally like looking into a mirror. If you put a group of people in a room full of mirrors and every single person can see their own reflection, that room is reflexive. Everyone relates back to themselves.
So, the crucial point is how this actually applies mathematically. The most perfect mathematical mirror is the concept of is equal to. A is equal to A. 5 is, well, equal to 5. A triangle is equal to the exact same triangle. Because anything will always be equal to itself, the relation is equal to is a perfect reflexive relation. It never ever fails to show an exact reflection.
All right, part 3, symmetric, the high five.
If the first one was a mirror, this next one is all about interaction. This is the symmetric relation. The rule here is a two-way street. If A is related to B, then B absolutely must be related back to A. Think of it like a mutual friendship or a high five. You can't high-five someone without them high-fiving you back, right? It requires mutual participation. If I'm connected to you in this way, you are automatically connected back to me.
And this brilliantly illustrates how we translate that physical high five into geometry. Take the concept of is perpendicular to. If line 1 is perpendicular to line 2, forming that perfect 90-degree angle, then line 2 is undeniably perpendicular to line 1. It's literally impossible for it to only work in one direction. It's a mathematical high five, a perfect two-way symmetric street. Which brings us to part 4, transitive, the gossip chain.
All right, we've arrived at the third and final type of the big three. Now, this is usually the trickiest one for students to grasp, but we're going to conquer it by framing it as a concept you are already incredibly familiar with, gossip. Let's define the math rule first to set the stage. A transitive relation states that if A is related to B and B is related to C, then A must be related to C. I know, looking at all those letters strung together can definitely make your eyes glaze over. But let's decode this visually.
Think about passing a secret down the line. Step 1. Person A knows a secret and tells person B. Okay, so A is connected to B. Step 2. Person B turns around and tells person C. Now B is connected to C. For this whole situation to be a transitive relation, we need step 3 to be true. Person A must be able to skip the middleman entirely and tell the secret directly to person C. If that direct jump from A to C exists, the chain is completely connected, and boom, your relation is transitive.
To really cement this chain reaction logic, let's just plug in some simple numbers. Our rule here is less than. If 2 is less than 4 and 4 is less than 5, then logic dictates that 2 absolutely must be less than 5. See that? The rule seamlessly skips the middle number, 4, to form a direct connection between 2 and 5. The gossip passed successfully from the start of the chain directly to the very end.
And finally, part 5, the grand finale, equivalence. So we've covered the mirror, the high five, and the gossip chain. Let's move to and see how this builds, because this is the moment where all these isolated rules finally combine into something much, much bigger. If you test a mathematical relation and you find that it acts as a mirror, meaning it's reflexive, and it acts as a high five, meaning it's symmetric, and it acts as a chain reaction, meaning it's transitive. If it does all three of these things at the exact same time, the whole shebang, congratulations. You've just unlocked the ultimate prize. You found what's called an equivalence relation.
Now you might be wondering, why does this matter so much? Because being able to identify and prove an equivalence relation is exactly what the CBSE exam absolutely loves to ask for. Proving a relation hits all three of those analogies is a classic question worth 4 or even 5 massive marks on your paper. And the best part? Now you actually have the conceptual tools to spot them instantly.
I want to leave you with a quick thought to chew on. We talked about social networks earlier, right? Think about friendship on a platform like Facebook. It's symmetric. If I'm your friend, you're my friend. But actually, it's not always transitive. My friend's friend isn't necessarily my direct friend. So my challenge to you is this. Look around your world. Look at your family, your community, even nature. What real-world relationship can you think of that is perfectly reflexive, symmetric, and transitive all at once? What is a perfect real-world equivalence relation? Keep looking for those connections, and I'll catch you in the next explainer.